Okay, so we will get into gauge blocks and steel wool this week. First, we'll get into the terms: precision, data record, discrimination, greatest possible error. Precision is like, imagine you're playing darts and you keep hitting the same spot repeatedly. That means you are being very precise. So precision is about being exact or accurate. So now we're dealing with the instrument in a lab, and each instrument, they have markings, and we call them the graduated units. And you will look for the smallest graduated unit, and that will be the degree of precision of that instrument. Okay, and of course I'll show you in the lab. So when you take a look at it, see, like you have different markings. See that? And here, this is the smallest graduated unit. See that? Of course, on this 1/32 scale, right? We have a different scale here, even though on the same instrument. And here, this is 1/16, see? And that would be the degree of precision for this scale on the same instrument, because this instrument, the steel rule, has two different scales. One is like 1/16 and the other one is the 1/32. Okay? The smallest graduated unit is right here, and that is your degree of precision. For 1/16, the degree of precision is going to be from here to here. Yeah? Numerical term is going to be that, so 1/16, because when you take a look at 1, you have altogether 16 units. When you take a look at from here to here, going 0 to 1, you've got 32, okay, units, graduated units, in between the 0 and 1. So I think now you get what is degree of precision on a steel rule. The steel rule have two different scales, okay? 1/16 and the other one is 1/32. Alright. In manufacturing, it's really important that we give the right amount of precision, because the more exact you want it, the harder or more expensive it is to make it. So when you need something made, like a part or a tool, it's really important to be as accurate as you need to be, but not more. And that's very important in manufacturing or industries. So it's better to ask for just the right amount of accuracy and not more than you really need. So that way you can save, of course, your time and money. The next thing that we need to know is the data record. A data record in the lab or here in metrology we're learning is like a note you would make to remember something important in your measurements, okay, in the lab. So like this, so your data 1 is here, data 2, 3, 4, 5. Suppose you're measuring the height of the plant every day. So that's your data, yeah, set from data 1 all the way to data 5, and that's we call a data record. Of course, you can use the data record that you have collected every day to analyze the data. Here, we're analyzing the average of that data. Alright, so discrimination is being able to tell the difference between tiny measurements. Okay, so right here you have a scale on your steel rule. It's like if you have a very small rule with tiny lines on it or markings on it. So your discrimination is how well you can see the smallest. See, this is the smallest space between these lines or markings. So the better you can see that small space, the more accurate your measurement can be. Okay. And for some people just try to remember, oh, from here to here is the discrimination. Okay, just make sure you understand the differences between the discrimination and the degree of precision of your instrument. Okay, degree of precision depends on the scale, and the discrimination depends on how well you can be able to see the difference between these lines. Okay, and it didn't mention it's got to be the smallest line, smallest, all right, smallest gap between the lines. And a lot of the people have confusion between the discrimination and then the degree of precision. Okay, so you can take it like discrimination, like resolution, okay, because it refers to the smallest unit or division, which is this little gap, right? And you can read it very distinctly, okay, and also you can use it to measure using this instrument. Of course, here we're measuring a part. So for a steel rule, this is typically the smallest graduated mark. Okay. So just telling you how fine a measurement can be observed directly on the scale. Okay. Degree of precision and discrimination, they're kind of related, but they're not exactly the same. Because degree of precision, on the other hand, it tells you, or refers to how consistently an instrument can give the same measurement under the same condition, of course. And it's also related to repeatability and reliability of the instruments, okay, or reliability of the measurements of that instrument. So it's a lot depends on the measurement you would have taken with this instrument for the degree of precision. Okay, so they sound the same, like the smallest unit, but the meaning, okay, the meaning is completely different. I'll just try to get discrimination as a resolution and degree of precision of the instrument, like repeated measurements that you would get by using this instrument. Okay, so you can take it like discrimination, okay, of an instrument. It's related to the degree of precision, but they're different because degree of precision involves other factors like the user's technique or the quality of that tool itself. Okay, so that's the degree of precision, and it's more about the consistency of the measurements taken by this instrument or the person, okay, who is using the instrument to take the measurement. For discrimination, it's just about the smallest measurement or smallest measurable increment on that instrument. Okay, so it's a totally different thing. The discrimination is more connected to the hardware, and degree of precision is connected to the hardware and the person who is using the instrument, and the person's technique using the instrument, and also the quality of the hardware itself. All right, so over time, if you think about the time factor, degree of precision depends on the time. Yeah, discrimination, of course, it's going to be that instrument and the smallest graduated unit on that instrument. And the time depends on, how long that instrument is going to stay, in the environment. Okay, I think you kind of get it now. So the greatest possible error depends on one's reading again. So here's a part and here's your steel rule, and you are measuring that part. And of course your precision, we will go straight to the smallest, right? Measurement it can done, which is from here to here, and that's a 1 millimeter. And your greatest possible error, I rated GPE for short, and that is going to be half of that precision. Okay, the smallest graduated unit divided by 2 is going to give you your error. The greatest error that you can ever have by using this instrument is 0.5 millimeters in this case. Okay, so for example, you read it, and let's say you can see it, and you read it like 12 millimeter roughly, even though it's like a 12.5. Of course sometimes you make mistake, and you read it like it's 12 millimeter. So we are going to add the greatest possible error, alright, value to our readings, and all you have to do is just go plus or minus off of that original reading that you've got. Okay, so that's a 12 millimeter reading, plus or minus 0.5 millimeter is your possible error that you would have committed. Okay, and so we now get a range, and that is 11.5 all the way to 12.5 millimeter. And we know that the accurate measurement, or the true measurement of that part, is going to be in that range, and it is. So 11.5 is right here, and then 12.5 is here. So the part itself, I would say the true value is 12.5, and it's still in that range. Even though you read it a little bit off 12 millimeter, it is still on this range, 11.5 all the way to 12.5. Okay, included of course these two values. So this is how we fix the errors or human errors that the operator or whoever doing that job could commit. Okay, and here's another example. Let's say you have a tool, and the die maker reads that tool measurement about 40 millimeter, and he uses a steel rule. So the smallest graduation on that scale is 1 millimeter. So we know, alright, the degree of precision is 1 millimeter, and then we're going to divide that by 2, so we get 0.5 millimeter. So if and his reading is 40 millimeter, so every time we give the report, we usually go 40 millimeter minus 0.5, and then 40 millimeter plus 0.5, right, millimeter. So the actual, of course, the actual length is going to be in that range. Okay, so that's 39.5 millimeter to 40.5 millimeter. So your reading is on it, and your actual length of that tool is also in this range. And now we'll get into the steel rule and gauge block. So these are the instruments you'll be using in your lab, and of course we will use both unit systems. The very first one is English or British, and the other one is metric. So gauge blocks, the same thing, English or British, and you're gonna have your metric. Okay, so we have 3 different steel rules. We have inch in terms of fractions, so we call it inch fractional, and the next one is inch in terms of decimal that we give the values, and the last one is the metric. So for inch fractional, we have, when you take a look at this example, we have a 116, okay? You can see the graduated unit. So from 0 all the way to 1, there are 16, okay, units. So if you think about the very, first, right, the very first unit, and that we will call it as a 1 by 16, all right, in length. So from here to here. So if you go from here to there, that is 2 by 16, 3 by 16, 4 by 16, and go all the way to here. 16 by 16 is going to make 1. Yeah, 30-second, 1 by 30-second, the same thing. From 0 all the way to 1, you have 32 units. So this little tiny unit right there is 1 by 30-second, right, in measurement, which is this length. Okay, so now you can see it. So if I go like 8 by 30-second, your length is going to be from here to there. Anyway, so you kind of get it. So inch decimal is a whole different thing, because even though they are in fraction, we use a decimal, right? Because it's easier for us to handle the values in a record. So here we have a 1 by 50, that's a lot. And from here to here, 1 by 100, your scale is. So this tiny little thing, we can't even see it, So that's about like 0.01, okay? This side, the tiny little unit right there is going to be 0.02. So instead of writing 1 by 50 and 1 by 100, it's really bulky to write. So we use a decimal instead of the fraction, okay? To make it easier for us to write. So 1 by 50, 0.02, 1 by 100 is 0.01, okay? So we know that that is the length of the smallest unit, and this is the length of the smallest unit on this side of the scale. Metric system use millimeters, So on this side we have 0.5 millimeter graduated units, and then on that side we have 1 millimeter graduated units, okay? So each graduated gap right here, which is your unit, okay, 1 unit. So you can count as a 5, 10, 15, and so on. So from here to here, okay, this tiny little thing right there, and that's a 0.5 millimeter, okay? Half of that, 1, okay? So 2 of 0.5 is going to make 1 of this. So from here to here, 5. From here to here, we have 10 units, okay? So anyway, so that's your inch, fractional, inch, decimal, and then your metric. So system, the inch fractional and the inch decimal is your English or British unit system. Your metric is your SI, Metrics unit system. I do want to correct a little bit, even though we loosely call metric and SI, it's only for the length, okay? Because we use the meter in metric, and also the SI, we use the meter, but they're not the same. They're not exactly the same system, okay? I just want you to recognize that SI is more like the international system of the units, and metric is like a decimal base system, okay? Okay, let's see how to read it. So here is your inch of fractional. So from here to here, we can look at the scale, right? This is 1 by 32nd, and this one is 1 by 16. So here is 1. From 1 all the way to here, you have altogether, okay, 14 units. Because from here to here is 16 units, right? That's 4, 8, 12. So 13 and then 14. Okay, so that's where you can see this. So 1 and 14 by 32nd inch. Okay, and that would be your measurement. Of course, we'll have to put our precision, okay, your greatest possible error. So we're dealing with the 1 by 32nd divided by 2 will give you 1 by 64th inch, okay, and that's your degree of precision here. And then this is your greatest possible error calculated, and you're gonna add plus or minus, okay, to your reading. Your reading is this, so your reading plus or minus the error, okay. So the true measurement, okay, the true measurement or the true length is going to be in that range, okay. Inch decimal will do the same thing. Then here is the part that we want to measure. There's 1, and it goes all the way, yeah. And this is 4, and of course it's about 3. We estimated it, so that's 1.43, okay. Because this is, that is 4.5 here, yeah, and that's 5, so it's got to be between 4 and 4.5. So we just measure it like, oh, that's a 1.43, and then we calculate the same thing. Your precision is 1 by 100, that's 0.01 in decimal, and we calculate the error, divide that by 2, and you would get 0.005, and your reading is 1.43, and we're going to put our error at the end with plus or minus, okay. So you get your reading plus or minus, that's your cover, which is your error, 0.00 possible error, so 0.005 inch. So the true value of this part, okay, would be in that range, okay. This is not the true value, this is your measurement value. The true value is going to be in that range, okay. All right, the next one is your metric. So your metric, we do the same thing, and your part is going to be from here to here, yeah, and we rate it like 50, and of course here 50, and that is 55, so there are 5 units on it, so we just go like, oh yeah, that could be like 51, about, yeah, 51.5, around there. So that's your reading. Your precision is 0.5 divided by 2 is going to give you 0.25. Put it plus or minus, add to your reading, and your true measurement is going, no measurement, your true, so length is going to be right in there, yeah, the true length of the part. Your part, let's say from here to here. Okay, so this is the exercise I want you to do in the classroom, okay, and of course we're trying to measure that part, and your reading is going to be, let's say 1, okay, and then 12 divided by 50, because this is your scale is 50 inch, okay, so that's from here to here 10, and then that's 1, 2, so therefore 12, and you have 50, okay, units in from here all the way to here. So every big I would say larger graduated, okay, the largest, you can say like the largest graduated unit, okay, consists of the smallest 1 by 50 unit on it. So your reading will be 12 by 50 inch. Your greatest possible error, we're going to divide the degree of precision, which is 1 by 50 is 0.02, divided by 2 is going to give you 0.01 inch, okay, and this is our reading plus or minus, and we're going to add and subtract the greatest possible error to it, and your true length is going to be in your measurement, okay, measurement report. Of course, your measurement always, you have to back yourself up by adding the greatest possible error that you could admit, okay. All right, every instrument, they have limitations, so your 3, okay, STI rules, so fractional inch, decimal inch, and metric system STI rules, they have limitations, and the limitations will go all the way to the smallest, unit that they can measure, and that's a 1 by 64, because this fractional inch can go only 1 by 64. This decimal inch STI rule can go 0.01, smallest, and of course the metric you can go 0.5 millimeter smallest. It means that it cannot measure below this, all right, length accurately. Okay. Then we learned something about gauge blocks. Of course, we'll get into English and metric gauge blocks, and also we will take a look at how to ring the gauge blocks together properly. This is your gauge blocks, the slip gauges. They were developed for the first time in early 1900s. Of course, we use them as standards for precision length measurement, because we measure, right, to make sure that we're getting the right length. They usually come in sets, and they're constructed from steel, hardened steel, or tungsten carbide, or ceramic materials. Okay. When you take a look at the gauge block, you have like two opposite faces. All right. Of course, they are flat surfaces, and of course they are perfectly parallel to each other. Yeah. Also, they have very tight tolerance. So when you're using gauge blocks in the laboratory, make sure you use them with care. You use your notes and supply how to handle it, okay, how to use it, and never use your gauge blocks without calibration. Okay. Of course, in the lab it's kind of loose, and we sometimes just go in and use it. We don't really do the calibration, but it is a good practice to calibrate before we use it. Ringing is like we can use these gauge block stacks up to, and of course including 50 millimeter, right? We can ring together. So you would choose the smallest length gauge block, and then you're gonna choose another level, right? So the next size up. So you have 2 gauge blocks, and you can build up a gauge block stack, meaning like you just put one on top of another. But before you do that, you're gonna clean the surfaces of both of your gauge blocks, and then you're gonna bring, all right, the faces into contact at an angle like this, about 90-degree angle to each other, and then you're going to press it down, so apply a minimum pressure at the center, and then of course slide it and then turn, right, 90 degrees. So the top gauge block is going to align with the bottom one, okay, like this. Okay, so first you start with 90 degree to each other, and then you're going to turn it so it's going to overlap on top of each other. And while you do that, make sure you apply pressure, right, onto the blocks, so that way they will stuck together, and we call that the gauge block stacks. Okay. Here I'm showing you 2 different shapes of the gauge blocks. So if the gauge blocks are in a good condition, and then the ring is going to take place very easily. But if they're contaminated, or you have, if they're contaminated, or you have like scratching all over or dirty, then it won't ring, okay, easily. So make sure you clean up the gauge blocks. This is what's in the box. So you have like of course we have variation, depends on the brand. This is just a standard, right, standard gauge block set, and you have like 9 blocks of 0.0001 inch series, and then you have like 49 blocks of 0.001 inch series, 19 blocks in 0.050 inch series, and then you have about 4 blocks in 1.000 inch series, and this is your smallest and that's your largest block. This is just show you ringing, okay? And if you look at this little video, then you can see that we are cleaning up, right, the blocks. And then the next video is going to show you, okay, this is the operator, and he's going to ring, yeah, the gauge blocks. We're going to apply the pressure and slide it 90 degree, and then turn another 90 degree, and it's going to, there it is, okay? And make sure you apply the pressure when you do that. Now you get the gauge stack, gauge block stack. Of course, the entire video we take it out from the YouTube, and here's your link, and you can also watch it. Okay, I'm not going to show it to you because it's 5.56 minute long. Okay, but you're welcome to go and watch the entire clip. Okay, so for now, if you get an idea of how to ring your gauge blocks, you're okay. First you clean up, and second you're gonna put on top of each other 90 degree, okay, kind of like a cross. So and then you're gonna apply the pressure, and then slide it as you apply the pressure, and then turn 90 degree so that the two gauge blocks will overlap on each other. Okay, so that's how you ring it. This is another YouTube link on gauge block ringing, and again you can be able to watch this is a little bit shorter video. Okay, and of course you can see this gauge is a hardened steel. The very first video that we show the gauge block is a ceramic. Okay, see like how he applied the pressure, yep, and then turn 90 degree. So this is a pretty clean gauge block, so they stack together, yeah, pretty well. So where we're using all these gauge blocks, we used to check the dimensions of the object, yeah. So when you take a look at it, here is you have a widget right there, and that widget is supposed to be like 1.489 inch high, plus or minus 0.003 inch, your error. So we're going to take the gauge blocks, and then we're going to make it a stack, right? And that is 1.489 inch high, because we know the length of the gauge, right? It's written in the box. So we know the length of that, and we gotta check, okay, your widget got to be 1.489 from the manufacturer specification. But we know that this two, okay, a gauge block stack is going to give you 1.489. We get that measurement from the measurement of this two blocks, okay, that comes with the box. So the box has a list of these blocks, and they give you the precise measurement of them. Okay, so when we stack it, we should get like 1.489. Okay, and then of course you're gonna put it to this dial gauge. Yeah, so we got the height, and then we're gonna put this widget into there, and then check if this widget really have 1.489 inch or not. Okay, right now it looks like this is it's pretty fine measurement, so we can really say by looking at it with naked eyes. Okay, you have to definitely put this into here, so you have a 1, 2, 3 blocks to make 1.489 inch height. Okay, and then we're going to put this in and then measure against the gauge block. So gauge block is acting like a standard. Okay, so that's the first application. We also use to check the calibration of the measurement tools. Then we use a gauge, see, for setup and adjusting the machines. Then we use setting the precise travel limits and your machine gaps. Okay, here is your gauge. So these are all the applications that we use. Okay, gauge blocks. So here is an example of your gauge block stack. So you can see, look at this, right? In order to make this 41.125 millimeter, we're going to add all of these blocks. So we have 1, 2, 3, 4, 5, 6, 7. Okay, when you started, there is no height, right? And then of course you're gonna go 1, 2, 3, 4, 5, 6 altogether, and then add it up, and you're going to get this height. So the height of the gauges are right there, okay? You can see each one of them. Here is the example of gauge block sets, and this side is your English and that side is your metric. Okay, this is your metric gauge block set, and of course this is a table, what's in there, and your size range, and then the quantities, okay? So you have 1 in this size range, and then 9 from 1.001 to 1.009 millimeter. Your unit is right there, and so and so. So you have 1, 9, 49, 49, 8, and 2 in this box, okay? This is your English gauge block set, and the same thing in inches, your unit, your size range, and then your quantities in that box, okay? So make sure you always use the minimum possible number of blocks, okay? Instead of using like tiny little things, about 6 or 7, it's better to choose, right? All different sizes to make it the minimum possible number of blocks in your stack. Okay, how to assemble? First, you're gonna clean, the block with the solvent. And sometimes in the lab we have the solvent, and sometimes we don't. So if we don't have it, then we're just gonna clean with the wipes, And then you're gonna make sure that you know which surfaces mate to other blocks. So this usually is the more highly polished surfaces they mate together, okay? And that's the reason why it's very important that you clean your gauge block. Sometimes if you are in doubt, you're gonna measure the block with calipers, and then you're gonna make sure which is the calibrated dimension, then you will ring them together one at a time, so they will stack together on top of each other. So cross the first two, the press, and then straighten it 90 degrees, turn it, and then cross the next one, and then press, apply your pressure, and then you're going to turn 90 degree another, and so until you get to the desired height. And then you're going to check the dimension with a caliper or a steel rule, So one of the students, I remember, he was asking how do you calibrate the gauge block, because the gauge block is service standard. You can calibrate by measuring with another standard like micrometers or calipers or something, okay? Calibration just making sure that they have the least contaminated surfaces, and they are, they have the exact or specification that's mentioned inside of the gauge block box, right? So it's kind of like a checking before you use it for measurements. So when we stack the gauge block together to make a height, we are going to select, okay, and it's got to be the minimum, right? Minimum number of blocks. So we're going to start with a digit at far right. So we're going to make a dimension, let's say 3.65075. So we're going to take a look at the far right digit, which is 5, okay? And you're going to find in your gauge block box, you're going to find a block that is going to match that number, the last number, okay? Oh, yeah, we found one, so that's a 0.10005, okay? So that's your block 1. And subtract that from your total height, you will get 3.55070. And then read this last digit, and that's going to be 0. Go to the box and choose the one that has the same ending, which is 0, So we got another block, block 2 is going to be 0.1007, okay, 0. Then you're going to subtract that again from the remainder, and you're going to get this, okay? And do the same thing. Check the loss, choose the block, subtract it, check the last digit, choose the block, and then subtract it. And when you get the remainder 0, you're done. So altogether, here somebody made a typo right there. So altogether you have 1, 2, 3, 4 blocks. Okay. And this is your gauge block box. So these are all the available blocks right in there. So you can be able to check the size range right here. This is just showing you step by step. Okay, first we check the end, subtracted, and then we go to the second step, so and so all the way to the end. And here we can see the whole thing. We started out, this is the desired height, your first block. The end gotta be the same. Subtract it, you get your remainder. Go and get the block with the same end, right? Same end means this digit is a 0, the last digit, and here the last digit of your block, your selected, your gauge block is also 0, and then subtract, check the end, choose the same end gauge block, and then subtract it, check the end, choose the same end, okay, gauge block, and you have 1, 2, 3, 4, okay, blocks stacked to each other. This is just your base, block 1, 2, and then 3 on top of each other is going to make this height, which is 3.65075. We're going to do the same thing for the inch system. Desired height, you're going to stack the gauge block on top of each other, okay, and you're going to stop when your remainder is 0. Metric example, 8.3250 is your desired height. We choose and select the gauge blocks. The minimum number of gauge block is better. And you're going to stop when the remainder is 0. And this is showing you step by step how to do it. And here is the entire calculations, okay? Desired height, selection of the first gauge, selection of the second, third, fourth, fifth, and the sixth, remainder 0, and this is your stack. And we call this gauge block stack. Your rule, you're going to always use the minimum possible blocks, and that's better. Because if you have too many, okay, here we have like a base, and then 4, we have base, and then 3, so this is better, stack. And make sure you don't invent gauge blocks that don't exist. It's got to be what's in the box. So you have to understand your tables, And of course, on homework and also exam, do not use your gauge blocks that don't exist in the tables. You have to use, depends on the size range, okay? Don't take it from someone else's box, right? It's got to be from your box within that range, and make sure you check the specification. Also, you have to check the gauge block, okay, value, which is written on the block itself, right? And that gotta be in this range. Now we're gonna come into our math review. We'll get into simple unit conversion. Just a review. We gotta know how to, go from English to metric, and then metric back to English. 10% difference calculation, your exponents, and your order of operations. Unit conversions, we're going to learn how to convert inch to millimeter, millimeter back to inch. So here is your inch, and then your millimeter, your steel rules, right? You're going to use them in the lab. So let's see how to convert units. We always use a standard, and that is your NIST unit conversion factors table. Of course, you will always get this one, alright, at your work. They will provide that for you. Here at school, we're going to provide this to you. So this is the guide for the use of your SI unit system, and here is our length. Okay, so we can go from inch to meter, centimeters, millimeters, kilometers, so width of mile. So we're not going to do that because we're in the steel rule, right? So only from here to here. So inch to meter, inch to centimeter, inch to millimeters. So we're going to pick an example, right? Because the method is the same. So the example, we're going to pick inch to millimeters and then millimeters back to inch. So our factors, right? The multiplication factor is 2.54. E is just 10. So when you read this, E plus 0, 1 means like 10 to the power 1, okay? Which is 10, of course. And I'm going to show you here. So we will convert inch into millimeter. We go to our standard table and we're going to get the multiply by value, which is 2.54 E plus 0.1. Okay, so that's what we take it out from the table. And now we got to convert 57 inches to millimeter. Write that down, 57 inches. Write this down, which is 2.54, okay, times 10 to the power 1. I write it here in details for you. This is short calculation. So 2.54 times 10 to the power 1 millimeters, okay, because we're going to millimeters, so you have to put millimeters. We start with inches, we're going to millimeter divided by 1 inch, okay. This is hidden, right? It's silent, it's always there. So 1 is always there, so 1 inch. Cancel the units out, so you're going to get 57 times this is going to give you 1447.8 millimeter. Give it like 4, this is 5 significant figures. Yeah? Okay. So to convert inches to millimeter, you're going to multiply the inches by 25.4 to get the millimeters. If we want to go back, you're going to divide the inches 0.03937 to get the millimeters, okay? But it's better that you stick to one rule instead of going crazy, okay? I would just suggest you to use this, which is multiply inches by 25.4 and you're going to get your millimeters, okay? So here I show you the detailed version of it, and this is a short version. It's not 2.54 because of the E plus 0.1 is going to give you 25.4 because this is 10. 2.54 times 10 is 25.4, okay? So don't forget that. Example, we're going to convert 1.375 inches to millimeter. We're going to write that down, multiply it by 20.5.4, you're going to get this. If you like to divide, you're going to divide it by 0.03937. But I wouldn't go with the division. Just stick with the multiplication for now, yeah? Okay, then we're going to go back 2 inches from millimeter. So we use the same standard. This time you're going millimeter to inches backwards. So therefore we're going to divide, okay? So we're given 88.7 millimeter. And we're going to divide with this number, which is 2.54 times e to the power 10, and which is going to give you 25.4. So this divided by this is going to give you 3.49212 inches. So let's take a look at in detail. So first we write down 88.7 millimeter, and then we're going to write down this, which is 2.54 e plus 0.1, 2.54 times 10 to the power 1 millimeter, okay? Since when you go from millimeter to inch, we have to divide, so we do divisions, okay? Sorry, I changed the I forget, yeah, because we're showing the detail. So instead of division, since we're dividing this with that, it's supposed to be here multiplication, okay? So 88.7 divided by 2.54 times 10 to the power 1 millimeter. So here are the details. You can see how your units are cancelled out, okay? So here it's a little bit difficult for you to see the units cancel out. So anyway, so units are cancelled out, and you're going to end up getting inch, so 3.4921, yeah? Okay, so 1 inch we have 25.4 millimeters, and 1 millimeters we have 0.03937 inches. Okay. You wonder like, oh, how did you get this number? All you have to just divide this 1 divided by 25.4 is going to give you that. Okay. So to convert millimeters to inches, you're going to multiply the millimeters with this, or you're going to divide millimeters with 25.4. We usually go with this second one, yeah? Divide the millimeters by 25.4, because when you want to change from inches to millimeter, we multiply. Alright? So pay attention when you study this. So here is your example. You're going to convert 14.25 millimeters to inches. Write down the millimeters you're given, yeah? And then you're going to divide it with 25.4 and you're going to get this, okay? Just try to remember one of them, yeah? 25.4 is easier for you to remember than this, yeah? So that's up to you. Then of course we have to get into what is a micron. So if you take out a dime, you're going to have a thickness of that dime, and that's about a millimeter, okay? So when you take a look at the thickness of a dime, and you will say that is approximately 1 millimeter, yeah? So that's a 1 millimeter. So the micron is a 1,000, right, of a millimeter. So that's a 1 millimeter. Again, micron is 1 by 1,000. Okay, so 1,000 of a millimeter. So what is 1,000 of a millimeter is kind of like slicing this thickness of a dime, okay, into 1,000 times. And that is micron. So each slice will be approximately 1 micron. Yeah, so if you have 1,000 micron, that would make 1 millimeter. Yeah, so a micron is 1 million of a meter, 1,000th of a millimeter. So you have 2.75 millimeter. That means you have 2 millimeters and 750 microns. Okay. Alright, how to calculate the percent difference calculation? So let's see. So percent difference, you will have to calculate this in your lab, okay? Because you're gonna have like a measure value. So if you had like the first measurement in inch, so let's say A, that's your first measurement, and then you have a second measurement, and we are gonna call that B, okay? And of course here we're giving a millimeter, yeah? Convert it to inch, let's say. So this is your inch, but that's a millimeter measurement, and then you convert that to inch. And then we have to find out, okay? Because we have to find out how far they are, right? From the first measurement. So percent difference is going to help you find out how much more or less your measurement, the second measurement in B, is now compared to what you had your first measurement in A. Okay, just looking how far they are. But of course, in the name is in percentage. Okay, so that's why we call it percent difference. So the calculation is like this: so B, second measurement, minus A, the first measurement, divided by the first measurement times 100. That's your percent difference calculation. Okay, and you're going to use this in your lab. Then we're going to quickly review the exponents. So we need to know exponent rules to compute the exponent. So the very first rule, okay, so x to the power m, x to the power n. So you have the same base xx. So at that time you can be able to add, all right, the exponents. So m plus n. The product of the exponent, all you have to do is add the exponents. The division of your exponents, all you have to do is subtract the exponents, okay? So here your base is x, your exponents m, and then n. There you're dividing this with this. All you have to just minus little n from the m, yeah? And here's all the example that we can see. So the first example, multiplication. So you add it up, 8, 9, 10, 11. See? Here you add it up, 4, 5, 6, 2 to the power 6. Same base, you add it up, so that's 5 and that's 5. Okay? Same base, division, you're going to subtract, so 5 minus 2 will give you 3. 3 to the power 5 divided by 3 to the power 3. You're going to minus 3 out of 5, and you're going to get 3 to the power 2. The same thing, same base, xy, 2, and that's 1. So 2 minus 1 is 1. 5 minus 3 is going to give you 2. Okay? 0 exponent, your base is x, your exponent is 0, will give you 1. Y to the power 0 is 1. 6 to the power 0 is 1. And this entire base to the power 0 will give you 1. Yeah? Even though you have a complicated base. So you have two levels of exponent, the inner base exponent and the outer base exponent. Okay? Power. So if you have x to the power m to the whole power n, all you have to do is multiply the exponents. So you have x to the power 3 to the power 2. You're going to multiply 3 and 2, and you will get the total power is x to the power 6. 3 to the power 2, total power is 4. So you're going to multiply that, okay? Two exponents, which is 4 and 2, is 8. So 3 to the power 8 is your answer. Z to the power 5 and the whole power 2, and you're going to multiply 5 and 2, and you will get z to the power 10. Okay? The next rule is expanded power. So you have expanded powers, all you have to do is just go in and multiply the exponent. Here is 1 and 1. Multiply by m, you will get x to the power m and y to the power n. Division, the same rule applies. All you have to just go in and multiply with the exponents in the second level. Yeah, so that's your first level inner, and then the second is overall exponent. So you will get x to the power m and then y to the power m. Your example, overall power is 3. The inner exponent is 1. We go in and multiply. Okay, we get 2 power 3 and a power 3. If you clear this out, 8 times a to the power 3. And we do the same thing, 6x3 multiply with 2, and you're going to get 6, 2, and then x3, and then 2. Multiply this, you will get 36, x to the power 6. Division, you go in and multiply 4 and 2, okay? That is going to give you 8, 4 and 1 is going to give you 1. You go in and multiply 2 to the power 3, x to the power 3, 3 to the power 3, y to the power 3 times 2, okay? So now you get 8 times x to the power 3, 27 times y to the power 6, okay? Negative exponents. So if you have a negative exponents like this, base x, power is minus m, so power is the same as exponent, okay? We call it power, so that's your exponents minus m. You can get rid of this minus, negative sign by dividing it, okay? So it's 1 divided by xm. So x by y, negative power minus n. We want to get rid of this little negative sign and change it to positive. We're going to flip the division. So y divided by x. Example, minus 3 is your power or your exponent. We want to get rid of this. So 1 divided by the whole thing, but now the positive, positive power. Here, get rid of negative 3, and now I have only 3. We're going to flip it, y divided by a squared, and then you go in and then multiply. We do the same thing on here. We want to change, the negative, so all you have to just flip. this one is positive, so we don't have to only flip the rest of the negatives, yeah, exponents. This, you have a negative power, 1 by, and then change it to positive, and then clean it up. Minus 4, x power 5, and x power negative, y power negative 2. This is the only negative, so we're going to change it and bring that to the denominator, yeah? And we do all the negative the same way, okay? And something that you have to be careful is when you have like negative x, don't think like you can change it into this, okay? If you have like a negative 3, don't think like you can change it into that. So because this rule is only for the exponent, the negative exponent, right? This is your base, right? So therefore the previous rule doesn't apply to this kind of situation. Minus 3 to the power 2, you can make this minus 3 multiply 2 times, yeah? And you will get 9. Minus 3 to the power 2. If you don't put the bracket like this, yeah, you can just square the 3, which is give 3 to the power 2, and wouldn't do anything about the negative, okay? So you will get like negative 9. So that's the importance of using bracket. So if you bracket it, it means like this exponent rule over the entire thing inside of that bracket. If you don't have any bracket, this exponent rules only the number that's attached to it, okay? Alright, so exponent 2 to the power 3, so your exponent is 3, your base is 2, meaning like we are multiplying 3 times, yeah? Negative exponent, we are dividing, okay, 3 times. So 1 by 2 is going to be like 3 times, okay? So 1 by 2 times 1 by 2 times 1 by 2 is going to give you 1 by 2 times 2 times 2. And if you solve it out, 2 to the power 3 will give you 8, and then 2 to the power minus 3 will give you 1 by 8. Yeah? 8 to the power 3, your base, and we're going to multiply 3 times. 8 to the power minus 3. Okay, now we're going to change this negative to positive. So 1 divided by the whole thing, but of course the sign of that exponent changes. And then you can give it 3 a's because it's said 3 times, yeah, 3 times. 1 times, a times, and then a. So 3 times a. And you're going to get exponent 3, and then your base is a, so your answer is 1 by a times a times a. This whole thing is under the bar, which is your numerator, okay? Don't forget that. Alright, we will take a look at with the numbers. So 8 to the power 7, we are multiplying 7 times, so you're 8. Yeah? X to the power y, yeah? Base is x, exponent is y, and we are multiplying that base, okay, y times 23 to the power negative 9, base is 29, exponent is minus 9, so we're doing 1 divided by 23 9 times. Minus 4, 5, base is minus 4, exponent is 5, you're going to go minus 4 5 times. Minus 5, minus 3, minus 5, minus 3 is exponent, 1 divided by minus 5, okay, 3 times. Minus 5 to the power minus 13, the base is minus 15, and then your exponent is minus 13, so 1 divided by minus 15, you're going to go 13 times, and that's whole is your numerator, and the minus 3 is your base, 3 by 2, okay, that's 5 is your exponent, so we're going to make this, alright, 5 times. Minus c is your base, a plus b, alright, is your exponent, so we're going to make minus c, okay, a plus b times. Minus 2 plus 3 to the power a plus b, solve it. So you will get like minus 5 for base, and you will go minus 5 a plus b times a times b to the power minus 6. Your base is b, a is just a constant, so you will get minus 6 1 by 6 times of b, okay, your denominator, and your numerator is your a. Minus a times b to the power minus 82. Your base is minus a and b, and your exponent is negative a by 2, so we're going to bring this to denominator and divide it by minus ab. We're going to go 82 times. Okay, so make sure you want to study this table so you get exponents. Okay, so now we have 1, 2, 3, 4, 5, 6, 7, 9. So your base is 9 and your exponent is 7. Your base is 4, your exponent is 8 times, right? Your base is 100, your exponent is 3. 1 by, so therefore it's a negative exponent. Your base is 95, 3 times, so negative 3. You have 4, your base is 4, and thus 4 times. And you have 9, your base is 9, and thus 3 times. We have 4, okay, 3 times, numerator, and we have 9, okay, 4 times, denominator. So numerator, the sign of the exponent doesn't change. Denominator, if you want to put it up, is going to be 9 to the power negative 4. Exponent became negative, okay, but this was like 9 to the power 4. 13 by 95 is your base, 3 times. 13 is your base, exponent is 1, okay. We want to bring 95 to the power 3 to numerator. So we're going to just put it up. When you put it up, you have to change the sign. So your positive is now negative, okay. So this is how you will solve the combinations of your exponent. Special cases, a to the power 0 will give you 1. A cannot be 0, okay. If you have like 0 to the power 0, that would be undefined. 0 to the power n, okay, would be n, look, you will have to look at the n. So 0 to the power n is going to be 0, but you have to think about what n is, yeah? So n cannot be less than or equal to 0. So if this n, alright, is equal to 0, it would be undefined. If this n, alright, is less than 0, which is a negative, right, it's going to be 1 by 0, okay. So when you look at this, you're going to get like 1 by 0, 1 divided by 0 is going to be undefined. So this got to be positive, right? So I wrote it here, n must be positive to get 0, right? So 0 n and negative n will give you undefined. Only the positive n as an exponent of 0 is going to give you 0, okay? So be careful around here too. Okay, now we get into order of operations. So this is another mathematics review. So you have to first solve what's in the parenthesis first. So if you have a parenthesis, make sure that you solve that before you ever get into other operations. Exponents, you're going to complete any exponent operations. So if you have an exponent, go ahead and do that first before you get into, yeah? So first you do your parenthesis, and then you're going to go into the exponent, right? That's the second, that's the first. Multiplication and division. So first we will clean out the parenthesis, second we're going to clean out the exponent, and then we're going to get into multiplication first and then division, okay? So division comes first in the example, and then complete the multiplication. Yeah, sorry, I said it wrong. So you have to do the division first and then complete it by the multiplication. So first you do the parenthesis, exponent, division, and then the multiplication. Okay, so complete any multiplication or division, whichever comes first. Okay, so if I had the multiplication before, and you can do the multiplication before and then the division later. Okay, so it depends on how they write it or how they arrange it in your problem. Okay, so it doesn't matter multiplication or division, whatever it comes first, you're gonna do it. So this comes first, so that's a division comes first, so you do the division first followed by the multiplication. And then your addition and subtraction, also whichever that comes first, all right, inside of your problem. So we clean out the parentheses, we clean out the exponent, we did the division followed by the multiplication, okay, and we're gonna do the addition, and then we're gonna do the subtraction, okay, and that's your entire answer for that problem. So 138, okay, and you're gonna solve it in the order of operations. So here we'll take a look at it. So first we're gonna solve this, yeah, because multiplication comes before the addition. So you get 34. We're gonna do subtraction, okay, and then we're gonna do the division, and then we're gonna do the multiplication. So why do we do the subtraction before the division? It's because it comes first, okay? Exponent followed by subtraction. Exponent, exponent followed by multiplication. Multiplication first because it comes first. Division, it comes first. And then finally your addition, okay, 51. Multiplication, subtraction, here subtraction, division, okay. Here's another review for your SI prefixes. So we're gonna use the powers of 10 that are whole, okay, multiples of 3 for this class, okay. So we will get rid of this 4 from the table. We don't need it for now, yeah, because they're not the whole multiples of 3. So here when you look at it, we can take 3 out of it, yeah, and you can write it this way: 4 10 to the power 24. So your exponent is 24. We're gonna break it apart. So 8 times 3 is 24, okay, and we're gonna take it on whole, power of multiples of 3, okay. So 10 to the power 3 is now our base, and then we have the numbers, right, to make this. So if you have like 10, your base is 10 to the power 3, and then your power is 8, we call it iota, okay. Power 7 zeta, power 6 exa, power 5 is Peter, power 4 is Tara, power 3 is Geiger, power 2 is mega, and power 1 is kilo, okay. So if you think kilo, that's base 10 to the power 3. Mega is base 10 to the power 3 of power exponents 2, and here are your symbol, okay. And we do the same thing. We're going to take the base 10 to the power 3, and these are negative exponents, so we're going to have that, right, because 3 times minus 1 will give you minus 3, and so on. So yeah, now we have the base 10 to the power 3, and they're in the negative exponents, so we're going to have a different names. The 10 to the power 3 minus 1, that is 1 divided by 10 to the power 3, is your milli, okay, milli. So if your base unit is meter in length, this is your prefix milli and then meter, yeah? So anyways, that's a milli, micro, nano, pico, femto, atto, zepto, and yocto, okay. So these are your SI prefixes based on the base 10 to the power 3. We have positive exponents and negative exponents, okay. And finally, we're going to review the notations. So we have two different notations. One is scientific and the other one is engineering. So we should know how to put the numbers in proper scientific notation and then in proper engineering notation. And then we gotta know and recognize the differences between the scientific and the engineering notations. So let's take a look at it. Scientific notation looks like this. So you have your number. So this is a non-zero digit, which is starting with 3 here in this example. Yeah, and then you have your decimal points times, and then you have a power of 10. Yeah, your base is 10, and then your power is 8, or exponent is 8. Okay. Now we don't have letters like MKN. Yeah, prefix, and this is your units, of course, in volts. So now we're going to change this into scientific notation. You count all the zeros. Okay, so that's 11 of them, and then you're going to place our decimal point right after the first digit. Okay, so the first digit is 5. We're going to place the decimal, alright, and then followed by everything else. And get rid of all the zero. We're going to put all the zeros, okay, as an exponent or power of 10, which is this. Okay, so we get 5.4, and everything, if you count it all together, this is 3339, and then that's 10 zeros. Okay, so you have 10 to the power 11, because you have 1 0. 10 is here. If you multiply that, you will get like 54, which is this, and that's altogether 9, and then 10, and then 11. Okay, why? Because we're placing a decimal right after the first digit, so that definitely produce the 11 0. Okay, so altogether this is 10 zeros. Since we're placing the decimal right after the first digit of your number, you will get another 0 for that place. Okay, so altogether 11 zeros. We have now the decimal is right after the 0 here in this example. So we're going to count all of the 0 again. So when you count it, okay, that's a 3, and that's a 3, it's a 6, and then 7, okay? And this is your very first number. After the 0 is 3, we're going to place the decimal point right there. So when you count all the 0, you have like, this is 6, is 7, 0. And since we're placing the decimal right after 3, so that this place is counted as a 0. So altogether 8. Okay, so we're going to put that power 8. Since your number started with a decimal, we're going to give it a negative, right? Negative exponent. So 8 zeros, so 7 0 with the 1 place, 1 place before the decimal, so that's altogether 8. So 10 to the power minus 8. Okay, so this is how you write scientific notation. So you have your number times, and then your base 10, and then your exponent. The exponent refers to the zeros. So if you have 11 0, you're gonna go, your place is 11, okay, after that decimal. So that's a 1, and there's no more numbers, so just add 10 more zeros, yeah, and that will give you your value. The same thing with that, 3.64, 10 to the power minus 8. Since this is minus 8, it will start with the decimal. We have altogether 8 zeros, so we go 7 0, and you have a 1 place here. You have a 1 place before the decimal, so I'm going to give that place 3. Okay, so you have 7 0, and then 3, and then 64. But that's a pretty standard way of doing it, but then of course you want to go with your own instinct, right? The way that we compute in our brain is very different, so you do whatever way you want to do it, but make sure that you write the scientific notation in this format. Okay, so scientific notation looks like that. In your decimal point, you have only one digit to the left of your decimal, and the first digit is always between 1 and 9. Okay. Your power of 10, which is this guy, is included, right? And sometimes it's 0. Okay. Units may be included after the number sometimes. Yeah. Meaning like you have like millimeters or meter or volt or blah blah blah. Okay. Right now there's no unit. Of course, after we're just giving you the numbers. So when you carefully look at it, see, of course that's positive, negative. You have one digit in front of the decimal point, followed by the numbers times. Okay. Your base 10 and your exponent. Okay. Exponent represents positive, then you add 0 there. So you will add 6 zeros after that. Okay. Actually, they already gave you 2 here, so you will add 4 zeros after that. Yeah. The 4, and then this is placeholder, so 5, 6. That's 5. So you would add 3 more zeros to it. Okay. For negative, exponent, you will start from 0 point, decimal point, and then you will add all the zeros, right? So now you're going to add 1 0, right, in front of this. You're going to add 4 zeros in front of this. Yeah, so 0.40 and then 670. Okay. Alright, so make sure you practice to go from here to there and from there back to here. And here I have, you can do it with your mind like I did, right, just right now, or you can write it down on a piece of paper to practice going back and forth. Okay, so you get a hold of how to count the zeros. Alright. Okay, we're going to count it, and here is pitch all, right? So you know how to count all the zeros. So you have your number right there, and we're going to change that into scientific notation. Scientific notation start with the 1 digit followed by a decimal. So we're going to start with the 5, the first digit, followed by the decimal, and your next digit is 4, and then we have to start with multiply by the base 0, base 10, and then we're going to count all the zeros. Yeah, when you count it, you have 10, and then since our decimal place is right after 5, we also have to count the place of this 4. Okay, even though it isn't a 0, we count it anyway. So that's your number 11, 0. Okay, so you will have 10 to the power 11, and you're going to write 5.4 times base 10, and then power 11 or exponent positive 11, and then your unit is m. Okay. So how do you read this? So here is your 1, the non-zero digit, which is 3, to the left, okay, of your decimal point, followed by the numbers times your base 10. Your power is going to be 8, which is your exponent, and then followed by the units. Okay, so this is what scientific notation looks like. Okay. Now let's take a look at the negative power, right? So if you have like 0 point and then 000, right, this type of number, we can turn that into scientific notation. So first, you're gonna find the very first digit number, which is, these are all zeros, so they don't count. So the first digit number is 3, yeah? So we gotta take that out, and then you're gonna put the decimal point right after the first digit, so 3 point, followed by all the number digits, which is 64, right? 3.64 times your base is 10, and now we're gonna count all the zero. We will start to count from the decimal point and count all the zero, and then you're gonna count the place of that digit, okay? Because we put the decimal right after that, so you also have to count 3. So that's altogether 70 and 13. So we're going to put -8. Okay, so your scientific notation is this, followed by your unit, which is gram. Yeah. Exponent, okay, you have to get the right exponent, right? So when you're dealing with a large number, the power of 10 is going to be positive, right? So the signs of the exponent got to be right. So this is a large number, but you check your sign, and that's positive. Small number, because it starts with a decimal point, right? Your power got to be negative, okay? And here we don't have it because it's an exact, 5 point, and then the values, and here also 1 point, and then the values here. So we don't need the power, for this case. You can leave it off. Now when we get into the engineering notation. Engineering notation is kind of different because we're using the prefixes, okay? So your prefixes are in letters, the table that we just studied. So here is a big number, and your unit is meter, okay? And we're going to put it in engineering notation. So we do the same thing, and first we are going to change that into scientific notation. And for engineering notation, we're going to start with 0, right, instead of the first digit number. So we start with a 0, and then we're going to put the decimal point, and then we're going to count everything. So when we count everything, right, you can count it like, remember the scientific SI, right, prefixes, we base with the 10 to the power 3. So you have to count from here, because that's your base, 10 to the power 3. So we go 1, 2, 3, 4, 5, 6, 7, 8, and then 9, okay? So we go back to this table, and we look at the zeros, and we found, see, 12 of them. So base is 10 to the power 3, yeah? So the first 3. So you get tera, yeah? So your prefix is tera. So that's altogether 12 zeros. So let's, and I'm going to show you, yeah? So this is 3, 6, this is 9, 10, 11, and then 12, yeah? So altogether exponent 12. So that's your tera. And I have to count 5 this time because we're putting the decimal right in front of the 5, okay? So the same thing we're going to do, we will put this decimal right after that 0, okay, right after that 0. Of course, here you can put the decimal point anywhere you want it in engineering notation, unlike scientific notation, okay? So the very first one, we put it like right before 5, okay? So now we're going to give you example. We're going to put this little decimal point right after 6, like 36.4. So now we will count, all right, the number up to this decimal, right? So that's 1, 2, 3, and then 4, 5, 6, and then 7, 8, 9, and stop, because we stop right after 6. So that's altogether 9 places, yeah? So 9, 10 to the power minus 9 is going to be nano, yeah? It's minus because we're going decimal to that side, okay? To the right side. If your decimal going to the left side, then it's going to be power 10 to the power is going to be positive. I mean positive exponent. Now your decimal is going to the right, right, all the way behind this number 6. So that's a -9 because the position that you change is 9 times. Yeah, so the first position, second, third, fourth, fifth, all the way to 9th position. So that's 36.4 nano, and then ohm. Okay, is your unit. And here are the examples that you can practice. So 1, 2, 3 digits to the left, okay, of your decimal point. So when you carefully look at it here, 41, this is 4, and here is 84, okay, and that's 2, and this is 230 point. So you can put 1, 2, 3 digits to the left of your decimal point, and that's alright. You can also start with 0, that is alright. no powers of 10. We don't have any powers of 10 like in scientific notation, okay? Right now we're using the SI prefixes, okay? So they are all letters, right? And they have a particular name, and all these letters and names you can get it out from the tables, yeah? And typically they include an engineering unit as the last letters, okay? So here your unit is going to be volt second, okay? Pascal is your pressure, right? Gram and ampere is your current, and then ohm so and so, okay? So you have prefix letter, and then you have unit, okay, letters or symbols. Be careful. So let's compare each other so you can see the differences between them. So scientific notation, okay, only one digit. Engineering notation, you can have many digits, up to 3. Start from 0, 1, 2, and 3. Scientific notation, just single digit, okay, before the decimal. We use a base 10 and then the power and then the unit. We use the SI prefixes and then the unit. Okay, these are letters, and this is also your symbol or letters. Example, and here is your example. Okay, this one is a kind of a mix because you can see the base 10 here. So that's a scientific and engineering. Okay, because we also use a kilo right there. So scientific and engineering notation mix here, and you can do like that. All right. Make sure if you want to show it the base 10, okay, you can do that. If you want to just show it the SI prefixes, you can also do that, but don't mix it like this, yeah. Even though a lot of people do that, yeah, but don't do it, because if you do it because you don't know about the notation, yeah, right now you know about the scientific and engineering notation, so it would be better you don't mix them up. Okay, so here are the two different ways to express the same value. So we have 6.43 times 10 to the power 4 volts. It's the same as 64.3 kilo, okay, volts. 4.332 times 10 to the power minus 4, okay, ohms, and you have like 433.2, okay, and this is your micro, and here is your unit, ohm. I'm coming back to this table to show you this little symbol, okay? So make sure you read the name and then the symbol, so you kind of get it, okay? These are very common, right? Commonly used, like milli, micro, and nano, we commonly use them. And on this side, giga, right? So your computer gigabytes all the time. Tera, we sometimes use it, okay? We definitely use a mega all the time, kilo, okay? So from giga to kilo, we use it all the time. So make sure you get the corresponding exponents, the power of tens. Now we're back to here, yeah? So 5.65 times 10 to the power 6, and then joules, and this is the equivalent engineering notation, okay? You have your mega and then your nano, 3.35, 10 to the power minus 10. We can write it 0.335 nano. You should be able to convert from here to there and from there to here, yeah? Just reiterating step by step. So we have 37.01 times 10 to the power 7, alright? Here is your milli and then your volts. Number 1, and this, okay? You're going to convert the first part, which is this guy. Scientific notation 3.701 times 10 to the power 1, right? And then times your second part, 10 to the power 7. And then we're going to change that into 10 powers. So this is your micro, so this is your milli, so it's going to be 10 to the power minus 3, okay? So now you have all the 10, so we're going to do our exponent, right, rule. All you have to just add them up, and you're going to get 7 plus 1 minus 3 is 5, yeah? So now you got 3.701 times 10 to the power 5 volts, right? So this is how you change your scientific notation from your engineering notation. Okay, you should be able to convert back and forth, so make sure you practice that. Okay, now we have scientific notation, and then we're going to change that into engineering notation. First, we have to get rid of this 10 to the power 5. So we're going to write that down, okay? In order for us to get rid of this, we got to find the right name for the SI prefix. And SI prefix is based on the 10 to the power 3, right? So therefore, first, we're going to make it combining, all right, all of your 10 powers all together, okay? So first we will move this decimal to the front, okay? So now we get 0.3701. So that is a one place going to the left, okay? So therefore we get 10 out of it, moving over there. So if you move to this side, you got minus 10 to the power minus 1. If you go to the left, you get 10 and then keep going. Yeah. If you move your decimal to the right, you go down. Decimal to the left, you go up. Right. So I go 10, one place up, so that's 10. If you go two places up, that's 10 to the power 2. Okay. So now we have 10 right here because the decimal place move, and here we have 10 to the power 5. So when you add it up, that's 10 to the power 6, which is, okay, your mega, yeah? So 0.3701 times mega volts, okay? Oh yes, I forgot to tell you about the significant figures, got to be the same. So we have 4 significant figures, so we keep the 4 significant figures here in our engineering notation. Okay, I wrote it right there. Okay, and then example 1 is showing you we're going to change, right, scientific and engineering mix, right, notation into a pure, engineering notation. First, we're going to change our decimal. So that's 10 to the power minus 5 going to the right, so minus 5 places, so 5. And then times 10 to the power 15. And this one is 10 to the power negative 6 because it's a micro. And you're going to solve your exponent, 10 to the power 4, so 5.4 joules. Now 10 to the power 4, you will have to choose the SI prefix, the right letter. So we don't have 10 to the power 4, because it's based on 10 to the power 3. So therefore, we're going to just get rid of that 1 extra 10. Multiply with that, so you get 54 times 10 to the power 3 is a kilo. Okay, so you get 54 kilojoules. Alright, the next one is example 2, and here we're going to change the engineering notation back. Alright, engineering notation, which is a mix with the exponent, alright, which is actually kind of is a wrong, improper, I would say, like improper notation, back to the correct notation of engineering, notation here. So now we're all mixed up here. We have like a pico here, and then we have like this exponent right there. So let's clean that up. So first number is here, and the second number is, it's at E, right? So that's a base 10 and 7 of them. So we go 10 to the power 7, and then I have one place, right? Because 7 is not a very good, right? Because you have to make sure that you get the base 10 to the power 3. So therefore, we're gonna take this, right, one place up. So move it to the left, so you will get 10 to the power 1. If you move it to the left, you got positive power. So altogether 10 power 1, 10 power 7. Pico is 10 to the power minus 12. So altogether, you're going to get 10 to the power minus 4, right? So minus 4 is not a good thing because we got to make it like the 10 to the power 3, either negative or positive. So we're going to take 10 to the power minus 1 out, multiply with that, so you get 0.2894, okay? And you will get like 10 to the power minus 3, which is your milli, okay? In this case, I would say like make sure that you go step by step, okay? Otherwise, you're gonna have a confusion between all of the exponents, okay? So make sure you also count the places when you move your decimal, yeah? So this 10 to the power 1 accounts for the move of your decimal to the left. To the left is positive exponent. If you move the decimal to the right, it's going to be negative exponent, okay? So the same thing here, see? I move my decimal to the left, so 10, and that 10 is cancelled out with 10 to the power minus 1, yeah? Coming out from here. So that's what you're seeing right here. Significant figures review. So if you have all non-zero numbers, they're all significant, okay? So that's 3 and that's 6. Zeros located between the non-zero digits, okay, are significant. So that's 4, that's 3, and then this is 16 significant figures. The trailing zeros, all right, they're significant only if the number contains a decimal point. So if you have like a trailing zero, they're significant if you got a decimal, right, in that number. So if you look at it, this is a very good example. So I have a decimal point after the trailing zero, so that's 6 significant figure, and this one, see, like it doesn't have a decimal point right there. Numerically, it will be the same value, but then positionally it won't, right? So this decimal makes a difference, right? Whether that's significant or not. This is not significant, okay? And here is only 2 actually significant, okay, figures, and this one have like 6 significant figures, but this decimal points out that we are going to consider all of this, right, zeros after 12 in this value, of course. Okay, so 0 is to the left of the first non-zero digits. So when you look at it, the first non-zero digit is this one. So all the zeros, right? We have to decide which one is significant or not. So they don't really count, okay, because they're only just like a placeholder, okay? So when you look at it, it has only 3 significant figures. This one has like 4 significant figures, and then 2 significant figures. Be careful with this one, yeah, because the decimal point is on the left. So therefore, we don't count all of the zeros, before 4. And the decimal point is not at the end. So make sure you don't count the 0 as well, yeah? So you gotta understand where the decimal point is. So the decimal point is right here, yeah? So therefore, we're not going to count it. We count everything is after the first digit of that value, so which is 4, 5, 6, and then 0. That's a 4 significant, right? Figures. Here, 2. And then this one, we don't count anything, and that's a 2 significant figures. So pay attention to this, and then pay attention to that. And like I said, you're not supposed to be mixing everything, but then you will see this type of notation that people are writing and outside, and but you understand how to read them, yeah? So E is a 10, and then these are power, positive power. That's negative exponent, or negative power, and that's a negative power or exponent, okay? And these are your SI prefixes, okay? It's kind of like a mix, right? Other notations. This is just trying to tell you how you use the SI prefixes and then your units, okay? That's your unit amps for current, and then that's your nano, your SI prefix, your exponent, base 10e, and then 9.4. Yeah. Of course, why do we have to introduce this? It's because we're going to use Excel, and your Excel, Microsoft right Excel system, they read it that way. Yeah. Alright, exercise is your homework. Lab 1 we're gonna start on Thursday, and then your math review exercise, please do. You're gonna turn in this, okay, to the Lab 1 assignment, and then you're gonna turn in this to the quiz, okay? So all of them you're gonna upload it to the quiz. You can take pictures and upload them, or you can scan them, okay, or you can type it in your Microsoft Word and change it to PDF, or just upload the entire Microsoft document. That's alright. So due date, you're gonna consult with the schedule that I gave it to you, right? I don't really change. Sometimes lecture is gonna be before the due date. It's okay. Yeah, lecture and labs can go faster, depends on your group. So your multiple files can be uploaded. So don't think like you have to submit only one time. No, you can upload it. Let's say like you finish your ISD rule exercise, you can upload one time, and then you can upload Gage block when you finish it, exponent order, operation, scientific, and engineering notation. So you can upload each file, alright, on different days. Just make sure that you don't pass the due date, please. Alright, that's it for today.